So can I start? Hello and good day to everyone. My name is Mohammad Arif Mahmood and I am a PhD student under Professor Marie Sklodowska-Curie. My thesis title is Experiments and Modeling in Laser Additive Manufacturing for Metallic and Ceramic Parts, a Correlation Study. So this thesis has two major sections, the experiments and the simulations. So every simulation model which we developed during this study was validated with the experimental results. And we started from metals and gradually moved from metals to ceramic parts. To begin, according to ASTM F2792, additive manufacturing is a technique to produce three-dimensional objects using a computer-aided design CAD model in a layer-by-layer fashion. So what we usually do in this technique, we develop a three-dimensional model using a CAD software such as SolidWorks. Then we convert that model into .stl file. It's a file format. And after that, we convert this .stl file into computerized numerical control codes, CNC codes in the form of G&M codes. And we use these codes to print my final part in a layer-by-layer manner. So one may ask why there is a need of additive manufacturing when we have conventional and non-conventional manufacturing processes. The first thing is that every conventional and non-conventional manufacturing process has its own standard operating procedures. They require tools, dies, and the molds, and they cannot print with a very fine resolution and cannot produce complex shapes. And furthermore, there is no design freedom. And every process is limited with a feedstock material. So all these possibilities are available in my additive manufacturing process. So the first thing is that this process is universal. So first we have to generate a CAD file. We convert the .stl file, the CAD file into .stl file. Then we slice this file using a slicer software and we print. They do not require tooling, dies, and molds. We can print parts with fine resolution and complex shapes. We can produce materials with various feedstocks. The design freedom is also available in additive manufacturing. And furthermore, there are two advantages available in additive manufacturing. The first one is that we can manufacture lattice or cellular structure, which is shown here at the bottom of the screen. And plus, the production cost is less in comparison to conventional and non-conventional manufacturing processes. So the additive manufacturing processes can be classified into direct and indirect additive manufacturing processes. For the direct additive manufacturing process, we usually use a laser beam to melt material, while for indirect additive manufacturing, we do not use a laser beam. Instead, we use a filament, a resin, or powder, slurry, or sheet. So this thesis is primarily composed on direct additive manufacturing processes, also known as laser additive manufacturing processes. So the laser additive manufacturing processes can be classified into two further categories. The first one is the laser powder bed fusion, which is also known as selective laser melting or selective laser sintering. So what usually happens is in this screen, we can see that there is a piston. The piston will move downward and the powder distributor will spread a layer of the powder particles. And the laser beam, which is focused via F theta lens, will melt the powder particles selectively. And means this is the schematic for the selective laser melting and the selective laser sintering. The main difference between the melting and sintering is that in SLM, selective laser melting, we completely melt the powder particles, while in selective laser sintering, we melt the powder particles partially or consolidation by solid state diffusion. In another schematic on the right hand side, we can see that this is a schematic for laser melting deposition process, also known as LMD process. So there is a robotic arm in this process a laser source, and the gases, which are usually the argon gas and the helium gas, and the powder distributor. So what usually happen in this process, a mixture of the gases will mix the powder particles and transport from the powder distributor to the nozzle beam output. And here the interaction between the powder particles and the laser beam will take place. And after this phenomena, the material will melt and resulting in the layer formation. So this is a typical setup of the LMD at Chetal in a Philip array. So in the figure A, we can see there is a disc laser source. In figure B, we can see that there is a KUKA robot, and there is a coaxial powder nozzle. Also, we also have the 3-jet powder nozzle, which is equipped on the robot, and a powder distributor. So the laser source in this setup is 1030 nanometer wavelength YB YAG laser source. It can operate in continuous wave and the pulse wave modes. And the focused laser beam spot size is 800 micrometer, while the distribution of the energy is super Gaussian, which results in top hat shape profile of the laser beam. And the laser source can operate in between 300 to 3 kilowatt power. So why there is a need to develop analytical models? First of all, it is very difficult to analyze which parameters are affecting my outputs using experiments. And if we cannot find out the one-to-one correspondence between my input and the outputs, it is difficult to control my requirements, what I need in my final product. So the second thing is that the finite element simulations are very time consuming, and their precision is based on the meshing accuracy. But in our case, using Core i7 8th generation 16 GB RAM computing system, the results were calculated in between 19 to 40 seconds only. And the third thing is that the analytical modeling with the real phenomena means what by incorporating all the happenings in the experiments, we can determine an optimum estimation. And after validation, these models can be used for the estimations and the optimization processes as well. So the first chapter, the first section in which we worked is related to the dimensions of the deposited layer and residual stress formation. And this work was published in the International Journal of Advanced Manufacturing Technology. So in this work, we developed model for the layer geometry and the corresponding residual stresses formation within the layer and the substrate. So for the residual stress formation, we identified two phenomena: thermal gradient mechanism, also known as TGM, and the cool down mechanism, abbreviated as CDM. So in the first phenomena, TGM, the laser beam rapidly heat my material, and a combination of rapid heating and the slow conduction will melt my material. And after the deposition, the material will try to expand, but the layer beneath it will hold it, which results in the compressive stress strain phenomena. While in cool down mechanism, CDM, when the laser beam moves away, the material starts to cool down, which results in shrinkage, but the layer beneath it will hold it, which will result in tensile stress distribution. So for the modeling, we assume some assumptions. We have some assumptions here. So first is we estimated that the powder to laser interaction point is equal to 25% of standoff distance. The standoff distance is defined as the nozzle beam, the power, the laser beam outlet to the substrate is defined as a standoff distance. And the width of the layer is equal to the width of the regime where the powder particles are melted. The third thing is the laser beam is attenuated. So what is laser beam attenuation? It is defined as that when the powder particles are added simultaneously with the laser beam, a significant portion of the laser beam is used by the powder particles to change their state from the solid to liquid. which will result in laser beam attenuation. And it is an inherent phenomena in LMD process. And the powder flow is steady state. So after these assumptions, what we did here, we estimated the dimensions of a single layer, the width, height, and the depth. Then we used the hatch distance to calculate the remelting depth and converted a single layer into multiple layers. And then we used this output to estimate the total residual stress formation within the layers and the substrate. So the equation 1, 2, and the 3 will result in the width, height, and the depth of a clad. The third equation will help us to calculate the total clad geometry. And the equation 4 and the 5 will result in the stress formation within the substrate and the layers. So after these calculations, we estimated our results and compared our results with the experiments and the numerical simulations as well. And we found out that our results were very accurate with respect to the experiments and numerical simulation, with a deviation of 10 to 15%. And all these results were calculated in 39 seconds only. So after addressing this area, we moved to the powder stream and thermal analysis in laser melting deposition. So this is the schematic of the figure A, is the schematic of the 3-jet powder nozzle. So we can see that there are 3 sub nozzles, E, F, and G. The powder particles will enter here and will interact with the laser beam at the point A. And at point A, they actually make a profile of Gaussian distribution. So for the modeling, we assume that all the powder particles are spherical, and we actually used a range of the powder particles, not just a mean value. The collision between the powder particles is neglected, and the laser beam attenuation is actually depending on the powder flow rate. After these assumptions, we calculated some equations. So the first equation will help us to calculate the powder flow in Gaussian form. The second equation will help to estimate the temperature distribution in the substrate when the powder particles are added simultaneously. And the equation third will assist to control the phase of the powder particles, which means that all the powder particles are melted entirely and none of the powder particle will enter in the plasma or evaporation. So we did some experiments in Chetal, and the figure A, the top image, we can see a profile of the Gaussian shape with respect to the powder stream. And after this one, we did some image processing to calculate these coordinates in order to validate our results with the experiment. And the bottom images are the results of the simulation model, the equation 1. So when we compared our results with the experiments, we found a very close correlation. And after that, we designed an analysis to identify what is happening when I'm defocusing my powder stream. So as I am defocusing, we can identify the 3 types of the powder streams: the Gaussian stream, the transition stream, and the annular stream. Then we compared the results with the experiment and the numerical simulations from some literature studies, and we found that the results were very efficient and were achieved in only 40 seconds with 10% mean absolute deviation. So after this scenario, we designed another case study to identify the effect of operating condition on the thermal distribution. So we increased the laser scanning speed, we increased the power, and we added the powder stream as well. And we identified that when I'm increasing the laser scanning speed, the laser to material interaction time is decreasing, which causing a reduction in my thermal distribution. While when I'm increasing the laser power, the laser energy density to material interaction is increasing, which will increase my thermal distribution. And when I'm adding the powder particles simultaneously, a significant portion of the laser beam is absorbed by the powder particles to change their phase, which will result in the reduction in thermal distribution arriving at the substrate. So after addressing this scenario, we moved to the microstructure formation and mechanical characteristics. domain. So in this domain, we determine correlation among operating conditions, microstructure, and corresponding mechanical properties. So the figure A, B, and C shows the SEM micrographs of AISI 304 stainless steel at 150x, 300x, and 600x magnifications. We performed 9 set of experiments. So from specimen 1 to 3, we changed the laser scanning speed. From specimen 4 to 6, we increased the powder flow rate. And from specimen 7 to 9, we increased the laser power. And after carrying out the experiment, we developed some cross sections and analyzed the SEM at the top of the deposit layer. So in the literature, I identified that when we are changing the operating conditions, the maximum effect of the operating conditions can be identified at the top of the deposited layer. So we performed SEM images, and we did some image processing using images software to calculate the average grain size and the number within a given area. So by performing the experiments, we identified that there are 3 types of the grain structures: quasi-continuous circular, long lathe shape, and the combination of both quasi-continuous and the long lathe shape. And further, we identified that when we are increasing the laser scanning speed, the grains are changing from the quasi-continuous circular to long lathe shape, which can be identified in the figures A to C in the case of samples 1 to 3. And when we are increasing the powder flow, the grains were changed from a combination of quasi-continuous circular and long lathe shape to quasi-continuous circular, which can be identified in figures D to F. And when we were increasing the laser power, the microstructure changed from the quasi-continuous to the combination of the quasi-continuous and long lathe shape, as presented in the figures G to I. Then this is a typical iron carbide diagram, and we used to identify the phases, what type of phases we have in our microstructure. So after comparison, we identified the perlite and the ferrite, which were developed during the laser melting deposition of AISI 304 stainless steel. We developed some models, and for these models, we have some assumptions. The first is the dilution rate is ignored. The dilution rate is defined as the correlation or the overlap between the deposited layer and the substrate. The powder properties were homogeneous, and the cooling of all the samples was done at the room temperature. So the equation 1 will help us to calculate the thermal history within the deposited layer. The equation 2 will be used to calculate the thermal stress and strain rate. And the equation 3 will be used to calculate the average grain size with the help of the JMAC model. And this average grain size was used to estimate the mechanical properties such as ultimate tensile strength, yield strength, and the hardness. So this figure shows a comparison between the simulations and the experimentations. So we can see from these images a very close correlation between my experiments and simulation. And further, we identified that whenever we are decreasing the laser scanning speed and the powder flow rate, we are getting the coarse and the grains with the higher dimensions. Figures A and C can be used to identify these results. While when I was increasing the powder flow rate, we found that the grains were more refined, means the dimensions of the grains were very less in comparison to laser scanning speed and the powder flow rate. After this one, we did some Vickers hardness testing to validate our results in terms of hardness from the simulation model and the experiments. And we found a correlation in between the experiments and the simulation with a deviation of 8 to 10%. And the model was able to deduce results within 19 seconds. So after this domain, we moved to the calibration curve of TI6AL4V and the corresponding pores formation within the deposited layer. So the Upper figure shows the tomography, X-ray computed tomography for the Ti6Al4b powder particles in axial, cross section, and the 3 dimensions, while the lower figure shows a distribution of the powder particles in 2 dimensions and 3 dimensions, and the classification of the powder particles with respect to sphericity. And we can see that the majority of the powder particles are in between 0.5 to 0.65 sphericity, while a few were in between the 0.35 and 0.5. So we developed a calibration curve by using this contour. We performed 15 experiments starting from 5 layers and moved up to 75 layers with an interval of 5 layers. And we developed the cross sections and took this cross section to the X-ray computed tomography. So the question is, why would we took this contour? So in laser additive manufacturing process, there are 2 types of melt flow pattern: the conduction mode and the depression mode, also known as keyhole mode formation. And what usually happens at the contours, when the laser beam starts from a straight line and arrives at the contour, so to accommodate this profile, the laser beam will slow down and it will transform from the conduction mode and the depression mode. So in depression mode melt flow, the probability of the pores is much high. So this is the reason we took this cross section and analyzed the X-ray computed tomography. And we identified that the pores were in the range of 0.630 to 0.725 sphericity with a diameter of 60 to 150 micrometer. And we tried to develop some relations among number of layers, identified pores, volume, diameter of the pores. And we identified that as I'm increasing the number of the layers, the mean sphericity is increasing, while the number of the identified pores, mean volume, and the diameter is decreasing due to iterative heating and cooling phenomena involved in laser melting deposition process. So we developed some models. So the first equation is for the height of the layer. The second equation will help in calculating the width of the deposited layer. The third equation will result in the depth of the layer deposited in the substrate. And the fourth equation will help us to calculate the dimensions of all the layers deposited on a substrate. And the last equation will assist in identifying the pores probability within the deposited layers. So these are the results for our calibration curve between the number of the layers and the deposited height. And we can see a very straight line between the 2 parameters. It means that our operating parameters were optimum. And this calibration curve is very important to estimate the number of the height of the deposited layer based on the number of the layers deposited within the LMD process. So to validate our model, we used some results from one of our previous studies in which we deposited parallelepiped using LMD process, and we analyzed the parallelepipeds with the help of the XCT. And we can see a very close correlation between the experimental and the simulation results with the deviation of 7 to 9%, and the results were achieved within 29 seconds. So up to now, we did some modeling and the experiments for the layer dimensions, residual stress formation, powder flow, thermal distribution, microstructure evolution, mechanical properties, and the porosity. And from here to onwards, we moved from the metals to ceramics. So, but there are different restrictions with the ceramics. The first one is the ceramics behave as insulators in comparison to metals. So if there is a ceramic which can be printed using laser additive manufacturing techniques, there can be 2 types of absorptions identified. The first one is the surface absorption, and the second one is the material absorption due to pores and the voids. So what usually happen, this is actually a schematic for the bulk ceramic substrate, and we can see that this is the absorption from the surface of the bulk ceramic, and What usually happens when a laser beam fall on this pore, the laser beam will have multiple reflections within the pore, which will result the final thermal distribution increment. And the second figure shows the schematic of the powder bed, and we introduce the voids in the powder bed as well. So the first equation will help us to calculate the thermal distribution in the bulk material. And we can see from the equation 2 that we also estimated the width to depth ratio of a pore within the bulk substrate. And the right hand side equation will assist in calculating the thermal distribution within the powder bed. And for the powder bed, we use the voids ratio, which is calculated as the mean powder area divided by the surface area of the powder bed. And we use this void ratio to calculate the thermal conductivity, density, and the specific heat. And of course, for these developments, we have some assumptions as well, that the bulk substrate has various pores. The powder bed has the voids, which were accommodated in both the modelings, and different values were taken for the materials when they were in the solid state and the liquid states during laser melting. So these are our results, which were achieved using simulations. And the left image shows the laser to material interaction when the laser beam is at the initial state of the substrate at 10 seconds. And the second figure shows the results when the laser beam has arrived at the end of the substrate. And we compared our results with the finite element simulations and the experiments. And we can see a very close correlation between the three. So the next figure is shows the result for the laser to powder bed interaction in case of alumina. And we compared our results with from the study of Qian et al. And we identified a very close correlation between the experiments and the simulations with an accuracy of 2 to 4% deviation. And the results were calculated within 21 seconds. And the upper figure here shows the thermal distribution across the thickness of the substrate and the powder bed. And after this one, we designed an analysis to identify what is actually happening when we are increasing the pore or void width to depth ratio. So we identified that as we are increasing the pore or void width to depth ratio, the thermal distribution of substrate and the powder bed is increasing. This is due to the multiple reflections of the laser beam involved when there are pores and the voids in the ceramic material. And the last figure shows the correlation between the scanning speed and the width of the melt pool and the depth of the melt pool and the laser power respectively. So we can see that as we are increasing the scanning speed, the width and the melt pool, the width of the melt pool and the length of the melt pool, both are decreasing due to lesser laser to material interaction time. And this, when we are increasing the laser power, we can see that the width and the length of the melt pool are increasing due to higher laser energy density to material interaction. So the conclusions are that in this study, we developed some efficient models for the deposition of layers, residual stress formation, powder flow, thermal distribution, microstructure evolution, and the mechanical properties, and the porosity analysis in the case of laser additive manufacturing. All the models were compared with the experimental results, and all the results were within the range of the 4 to 15% deviation. We performed experiments for AI-Si 304 stainless steel and TI6AL4V materials. We performed scanning electron microscopy and the hardness test for AI-Si 304 stainless steel. And another thing, we developed a calibration curve between the number of the layers and the deposited height for TI6AL4V. After that, we performed some X-ray computed tomography on TI6AL4V material, and we identified that the XCT is a very attractive tool to analyze the defects and the pores within the deposited material. Then we developed the laser to ceramic interaction models in case of the bulk and the powder particles by including voids and the pores within the modeling. And for the future work, We will work on the ceramic reinforced metal matrix composites. So this is actually a mixture of the ceramics and the metallic powder particles, and we really mix and print. So up to now, there are some conventional manufacturing processes, but they need some post-processing techniques as well, which are very difficult using traditional techniques. So one of the solution is to print them using laser melting deposition. And the second thing is, which we will focus on the latest structure. So the latest structures are usually lightweight. They require less time to manufacture, and the material is also safe. But on the other hand, they have excellent compression strength in comparison to bulk materials. But with the LMD, there is a limitation that we cannot print the very fine latest structures with the laser melting deposition equipment. But on the other hand, it has a very flexible scanning head, which if we can solve this problem, it will be very beneficial for the LMD community. The third thing is, which we will focus on, is the topology optimization with 3D printing processes. So what we usually do in this software, we define the part dimensions, limitations, and the load which has to be applied. And based on all these inputs, the software will calculate a new shape. And these shapes are the optimum shapes which can withhold all the loads applied and the limitations, but they are convoluted and they can only be printed with the 3D printing processes. The fourth thing is that we will develop some models such as artificial neural network models, and we will link them with the 3D printing processes. So the simulation is a very hectic process because it involves lots of equations, multi-physical equations. But on the other hand, the ANN, artificial neural network, they usually identify a correlation between the inputs and the outputs based on the data provided. And they can also be used for the estimation and the optimization of the process parameters. So during my PhD, I published almost 12 ISI papers with the cumulated ISI 33.379 and AIS factor 5.142. Besides this, I attended 4 international conferences and one national conference. And these 3 articles are under process. So during my thesis review, there were some questions asked from Professor Dr. David GROSSIN. So first question he asked, could you define melting, partial melting, and sintering in the first step? Yes, of course. In the literature review, actually, the melting term is usually used for the selective laser melting process, and the partial melting is used for the selective laser sintering, or another term is the consolidation by the solid state. The second question was, for each modeling, could you indicate the computation time? So for this study, we used a Core i7 8th generation 16 GB computing system, and the model which was presented in the chapter 2, it was able to calculate results within 39 seconds. The model in the chapter 2 gave the results in 40 seconds. The model in the chapter 3 generated the results within 19 seconds. And the model in the chapter 4 gave results after 21 seconds. While the last model in the chapter 5 yielded the results within 29 seconds. So the question 3 was, could you combine models in chapter 2 to 6 to fully modeling additive manufacturing processes? What are the advantages and disadvantages of this combining model? Yes, of course, we can combine all the models to generate a cumulative solution for residual stresses, powder flow, thermal analysis, average grain size, mechanical properties, and the porosity. So using this combined solution, one will be able to calculate the solution with a single command. But on the other hand, the computational time will increase. So the question 4, he asked, what are the technological locks for creating a new commercial product using the modeling? So actually, all these models are user defined and based on the material properties and the operating conditions. So if we want to launch a new product, the most important thing we need the material properties and the operating conditions. And these models can be used to optimize the process parameters before performing the actual experiments. This will save the cost and the time for the experimentation. So in the last chapter, could you describe more the artificial neural network? Is it what you did in the two of your articles listed? Yes, actually, various data-driven models known as machine learning have been provided in the literature for the 3D printing. So as I mentioned earlier, that if we are using the artificial neural network, there is no need to use the multi-physical equations. And they automatically learn from a correlation between the inputs and the outputs based on the data provided. So the machine learning can be classified into two subdomains: supervised and unsupervised machine learning. So ANN is actually the supervised machine learning, which has three subtypes: multi-layer perceptron, convolutional neural network, and the recurrent. So the last two, convolutional and the recurrent neural network, they are used for the image processing. And because the convolutional neural network will transform the image in the form of the matrix, and the recurrent neural network has the capability to read this this matrix. Yes, in the article 5 of this thesis, we used all these approaches. In the first article, we developed a literature study based on the 3D printing technologies, the introduction of the ANN, the applications, the challenges, and how we can resolve these challenges with that in the field of ANN by combining ANN and the 3D printing. And we identified one problem during the literature study, that for these ANN, we usually need a huge amount of the data set, which is not feasible using experiments. So how to solve this problem? So one way to solve this problem is to link the modeling with the ANN. So we will develop a model, validate the model with the experiments, and use the model for the training of ANN. And this case study was provided in the article 1 of the PhD thesis as a proof of concept. Thank you so much.